The next surface function is surface curvature. This has been described by some as the slope of the slope. What it's doing is it's describing whether or not the surface is convex or concave. In other words, whether or not it bulges out or kind of sinks in. What I have here is a slope shown, which we have one point or other points. We calculate the slope, but we know in reality, slopes are much more complicated. We have areas in which it bulges out, comes back in, and then bulges out, and so forth. What we can do is we can relate curvature to a wide variety of environmental processes. To use just one simple example, we know water moving across the surface will either erode or remove material, or deposit and lay down material based on the speed at which that water is moving. Faster water is more of an eroder or a remover, let's say, whereas slower moving water is more likely to kind of lay it down and deposit eroded away material. What I have here is a cross-section view of a surface profile, and we know that the steeper gradient up here is quite obvious, and then it gets quite shallow. So this is kind of a cross-section view, a profile view. And we can expect the erosion to occur up here, and then the deposition to accumulate in this particular zone. So then this is ways in which we go ahead and model this, so we can go ahead and predict amounts of or rates of erosion, amounts of deposition, but we can also then use the real surface to see kind of a post analysis of how much erosion, how much deposition has occurred over time. So the moral of the story here, what I'm trying to emphasize is not every slope is linear. And even further, not every surface is curved the same. What we have here is at the top, we'll think of it, let's go through the rows. Each of these have a same pattern here. Notice the curvature profile is the same. Whereas here, kind of more of this kind of a shape, more like a skate park, let's say. Then here, straight lines. Whereas the columns are different. Columns are showing, in this case, separation. This case, convergence. Notice how the arrows are coming together, whereas here, straight lines in which they remain parallel the same way. So let's do an example of a curvature profile. And once again, we'll be using our DEM from Story, Indiana. And we have our input raster being that DEM, our output curvature raster. We'll have a kind of a combination of these two here at the bottom. And these two at the bottom are important because it's what I'm going to talk about next. And it's profile curvature and plan curvature or planform curvature. Once again, we have the z factor, and this would be important if the x and the y were in meters and the z were in feet. We want to then compensate for that here in the z factor. So now we're going to focus in on that first one, the surface profile curvature, the profile one. And what this does is this depicts change in slope in the direction of the maximum slope. And so what I mean by that is the maximum slope is going this way in all three examples. And we're looking at the curvature profile in that same direction as well. So this is going to be more relevant to those that are related to acceleration and deceleration of flow, which of course is going to relate very much to the previous example I used of erosion and deposition. I just want to use this slide to kind of introduce some terms. And so we'll say that this particular area, to use terminology, I'm not the one that came up with this term, but upwardly concave, which is also known as concave upward. So think of it like a cup, and so it would hold water, let's say. So concave upward, C up. Think of a cup as a kind of an analogy here. So we also think of this as areas in which slope increases, whereas we have in this case an upwardly convex shape. So this is where slope decreases. So think of it sort of like a roller coaster. Where on here would we see speeds be faster than what would be the average speed of the roller coaster, and where would we see slower speeds? And so it's just kind of imagine we're kind of going along, then the acceleration happens, and then you get to this point and it starts to slow down again. And so where you see the faster amounts of erosion happening is going to be, of course, on these steeper slopes in these particular areas here. And so this, once again, is how we can relate this to the whole idea of areas of accumulation, areas of erosion, and the previously used examples. So once again, using those terms, this particular one would be upwardly convex, this one would be upwardly concave, and this here is linear and constant. And one of the things is when we put this into a GIS, we get an output. And that output cranks it out at the cell, obviously at the cell or the grid or the pixel level, and produces either a positive or negative value, or even sometimes zero. And so a positive value in the profile curvature output grid indicates that the grid is upwardly concave at the cell. The higher the positive number, the more upwardly concave a cell is in relationship to its neighbors. Once again, think of this, the cup analogy, as this particular learning device. A negative value in a profile curvature output grid indicates the grid is upwardly convex at the cell. The most negative value indicates a more upwardly concave a cell is in relationship to its neighbors. A value of 0 indicates the slope is constant. This is the output from the profile curvature that we created. Let's take a look at the values first. We see positive and negative. And so black are shown as negative and white shown as positive. And once again, going back to the previous slide, positive, upwardly concave, more of a cup kind of a feature. So we think about this. Does this make sense? The white areas that we see here, do we see this relating to a cup-like feature? Of course we do. This is where the rivers are. These are where all the water that comes down the slopes collects into very much a cup-like shape that we think of as being streams, rivers, river valleys, creeks, and ravines that then, of course, flow to a bigger location here where we have another cup. The profile curvature, what this does a really good job of doing is it showcases kind of a terraced, kind of looks like contour lines, but kind of shows the terraced looking pattern here. We do have some areas where we have some distinctively upwardly convex shapes. That would be up here at this particular point where we have negative values. And so that's where we're going to see more of a shape that's opposite of a cup. So this is a particular point that's quite noticeable here where we have some serious amounts of curvature. Now let's look at the other type of curvature, planform or plan curvature. This depicts change in slope perpendicular to the direction of maximum slope. So beforehand, we're kind of concerned with the side view. And so once again, we think of this as being the maximum slope is going this way. Perpendicular to it would be at the top here. And so notice now we have different shapes, kind of different convex and concave shapes compared to the linear. So beforehand, we were looking at the side view. Now we're kind of looking at the curvature from above. So what this is going to be is a little bit more in terms of the directionality in terms of the flow across the surface. Beforehand, that one was more about acceleration, deceleration. This here is going to be more as far as the direction. Do we have flow that's divergence? Do we have flow that's convergence, or is it linear? And if we look at the side view, in all of them, they have the same profile curvature. They're linear, but they have different curvature characteristics in terms of the face. Option A over here has the curvature most akin to the human nose. Think about the human nose, the bridge of your nose. Whereas option B is more akin to a slide at a playground, and it's more what you're going to see in a river valley or a glacial valley. In terms of the output grid, the one option A, where we have divergence, there's where we're going to see positive values in the output grid. Areas where we have convergence, where we have flow coming together in terms of its direction, we're going to see negative numbers, and of course 0 being where we have a linear or constant. So going ahead, before we even click onto the output grid, we should go ahead and expect that negative values, in this case they're going to be shown in black, using that same color ramp, we should expect those rivers in those creeks in those valleys where we have flow coming in to really stand out, and we most certainly do. Once again, we have our curvature grid, so those places in which are shown in negative are black and positive are shown in white. So we can see very clearly those rivers. And so the case of the profile curvature, it's good for showing the terrace kind of effect, whereas in this case, the planform is really useful for showing the rivers, the ridges as well. We can see the ridges right through there is a good example of a ridge, but we can see areas of convergence. And so what I did here was I just combined the two. We got the profile curvature at the top, which once again is really good for showing the terraces kind of showing that kind of that effect, whereas the planform curvature much better with the ridges and the valleys. So those valleys where we see convergence very, very, very clearly shown. And it's all kind of, once again, what's your objective here? So what you can do is you can mix these with something I'm going to talk about later, hill shade techniques, hill shade effects, to create a variety of cool looking ways to look at the surface and view the surface. And so this does have some analytical capabilities, but also can be used to add some visual enhancements to a particular surface. What we're going to do is we're going to mix these two, and that's what essentially when we create an original curvature grid, what it does is it just combines the best of these two. And this here now is the curvature grid, the original one, the kind of the output. If you do just a straight up curvature, show me the curvature, combines both the plan and the profile, so it's a combination of the two, and we have once again positive and negative values. Let's go ahead and we'll zoom in, we'll go 3D. So what I also did was I changed the colors, so instead of going the black and white, and so now negative shown in blue, and red shown in positive. And so what I did was I put it into 3D. And let's go ahead and we'll compare it to the slope to kind of get our perspectives right, since we just talked about slope in the preceding video. So we talked about areas where we had steeper slopes, more flatter, more gentle. So these gentle flat areas here where this is where the stream valley network comes right through here, the drainage network. And so let's look at it in terms of going back to, once again, our curvature grid. And so here, once again, areas of red are areas in which we see kind of the tops of these ridges. Notice the shape. We have a upside down U shape, that ridge shape, whereas the blues, the negatives, are where we see more of a cup shape. And so that makes sense that we're going to see more of that cup shape where we have the stream valley network located, and we're going to have more of the red areas, the upwardly convex areas, are going to be shown at the tops of these ridges. And so this is a way to kind of get a perspective of the curvature grid overlaying on top of the 3D DEM that shows the terrain. And it kind of gives a better perspective than maybe that black and white color ramp. So the moral of the story in this slide, both the red and the blue show curvy areas, but they're just describing different characteristics. The red show upwardly convex, whereas the blue show upwardly concave.